Okay, we are just over half of the responses, so we're going to go ahead and end the poll, and I'll share those with you. The first question is, how familiar are you with the concepts of uncertainty quantification? And this is split right down the middle. Half are considering UQ or uncertainty in their research, and half don't currently but plan to include it. So this is a really important topic, I think, today. And then the next question kind of split all over. There are topics of UQ or optimization that are of interest across the board from, I don't need to list them, but each topic has at least one vote. And our third question, kind of what UQ method are you most interested in HydroUQ? Half have responded that they're interested in forward analysis. 25% said reliability analysis, and we had one vote for each of global sensitivity analysis, and one person said there aren't any topics that they're interested in at this time. So thank you for those responses. And now I invite Sangri, a postdoctoral scholar at UC Berkeley, to go ahead and begin.
Thank you, Matt. Hello, everyone. So I'm Sangri. I'm developer at SimCenter. Me and Aakash, I and Aakash are working on UQ aspect of the tools. So in this slide, in this session, I will first talk about like interface between HydroUQ and our UQ engine, which is Dakota. And then later on, Aakash will give you a brief overview on the UQ options we have in HydroUQ. This is very brief review on our center and our tools. So SimCenter develops open source software, like open source and extensible software tools for researchers in natural hazard engineering. So our tools include these 6 tools. And depending on which type of natural hazard you're interested in which level of response, you can select one of those. But all of these 6 tools shares the same scientific workflow, which is represented in this right-hand side figure. So here you see this positive, we represent it as kind of jigsaw puzzle pieces that to emphasize that we can, this is highly modularized. So you can replace some of these puzzle pieces to fit in your needs. And our workflow management system is represented by this figure of single puzzle piece. So for each modules, we use those apps that are already available in our community. So what we do is create this post-processor and pre-processors so that each different application can be assembled to each other and make like one big flow. One thing to point out here is that we are not aiming for deterministic workflow. Instead, we are running UQ workflows. That means for some of these parameters in the models, we can set them as random like variable, and therefore our output will also be some kind of random quantity that can be characterized by mean or standard deviations. Therefore, for the user's perspective, they need to provide more additional information, such as like distribution of parameters. And in perspective of workflow, it requires multiple simulations of this whole flow for like different combination of parameters, that like different combination of possible parameters. Therefore, it can be computationally burdensome. And we try to overcome this using HP resources and in UQ aspect by implementing efficient UQ algorithms. So this is again a brief map of our 6 tools. The below here is external application, which are the core parts of the previous puzzle piece. And then there is backend components that wraps around this core part. So by assembling these puzzles, we first have like basic level application, which is Quantification, that focuses on UQ analysis. So this is most general tool. And then there are 3 more applications specific to each hazard type. But all these 3 applications aims to estimate the structural response subjected to each hazard scenarios. And then PBE application additionally adds this damage and loss modules for performance assessment. And then there is regional level risk assessment too. So this R2D and HydroUQ are newly released, like our newest application that completes our figure. So if we only see this hydro part, we can see that there are 3 components that are like pillars of this application. So first one you learned through previous sessions, RCFD simulation module that generates like in tsunami and inundation scenarios. And then there are structural module that gets this load profile and runs structural simulations. And then there are UQ analysis module. So if we convert this figure into this puzzle, again, this puzzle figure, so the first piece here represents the event generation module, which focuses on hydro. And then these 3 parts are the structure part. And then there are UQ parts that wraps everything around. Here I represented this, I draw this dotted line for those parts connected to event, because our workflow originally also covers event inside our UQ workflow. That means we can make event random as well. But in current like version 1 of HydroUQ, it is not yet supported. That means we can set random variables only in structural properties. So this is because of some difficulties that CFD simulation can take easily 20 hours to run a single simulation. So so what we need is to propagate this uncertainty in events with minimum number of simulations. So that's what we are currently working on, and it will be implemented in the future release. So other than that, currently we have UQ engine that is based on Dakota application. So here I will give you a brief explanation on what is Dakota. So Dakota is an independent software that is a general purpose toolkit for uncertainty quantification and optimization. So it is developed by Sandia National Labs. So what Dakota does is to interface with any kind of computational model that user provide and run the UQ analysis and give the user a result of UQ analysis. So those analyses include like sampling reliability and optimization and sensitivity analysis and modes. There are like other broader choices. And then, yeah, and this application is distributed in open source form. And here in our HydroUQ setting, this computational model will be replaced by our workflow, the workflow HydroUQ has generated. So if we see that in detail, HydroUQ consists of 2 parts, which are first front-end user interface and back-end applications. So every information we put inside HydroUQ frontend are saved as a single text file, which has like JSON file format. This is one of the file formats that are readable. So if you open up the text file, you can see the actual variable what we have written in the input sections. And then what Hydro does is to translate this into Dakota, the file format that Dakota can actually interpret. So once this is done, it also generates this workflow driver, which are like collection of scripts that runs all this, each part of simulation and connects them. And then once we are ready, we run Dakota and get results and display in HydroUQ. So if we see this user interface in more detail, we have different panel selections which correspond to each puzzle pieces in the previous figure. And here, event type corresponds to the CFD simulations we learned in session 2. And also we will practice tomorrow. And there are also other 4 parts which focuses on the structural analysis part. So this will be covered in detail tomorrow. And then the remaining parts are uncertainty quantification tab and random variables tab that we are interested in. So first is UQ tab. So here we select which analysis we want to run. First, we have to select UQ engine. Currently, we only support Dakota, but in the previous figure, there was like lower level application which was called Quantification, and in that program we have more engines that include surrogate modeling module and calibration modules. So we plan to gradually implement those engines in our HydroUQ as well. But at current stage, only Dakota is supported. And among the Dakota method, we support forward propagation, sensitivity analysis, and reliability analysis modules methods. And this will be covered in more detail later on when Aakash speaks. And then there's random variables tab. Once you select what UQ method to run and put all these models in each tab, when you define your model, you will also have to define which parameters will be considered as random variables. So for this, this can be done in several ways. For example, if you use our building model generator, you can do it through our user interface. So here, instead of by putting like string character instead of numbers, HydroUQ can identify like this is random variable. And another thing, if you want to directly read model script, directly read model from your own script file, then there are also some commands that HydroUQ that helps HydroUQ to identify which are random variables. So in most cases, if you do it in this way, this random variable tab will be already filled with the variables you had defined. And the remaining is to set the distribution types and their parameters. So currently we support 6 different probability distributions, which are widely used in this field. And one thing I wanted to mention is that even though it is the same distribution, there can be like different ways of parameterizations. So the thing I recommend is to, before defining parameters and putting in the parameter values, please check our manual and make sure that the PDF parameter you are thinking corresponds to the PDF parameter we are providing. And another very good practice is to check the PDF shape of the value which you provide. So there is show PDF button that shows you the PDF corresponding to your parameters, and you can double check that the mean and their variance range are in a like correspond to what you had intended. And these 6 probability distributions are selected because we think it's widely used in natural hazard simulations. But if you have different needs, or if you have any ideas related to UQ or HydroUQ that you think it will benefit our community, we are always happy to hear about that. We always love to hear from users. So please feel free to communicate with us using our SimCenter forum. And these slides contains very brief descriptions for each random variables, especially for those who are not really familiar with how to deal with randomness. So first one is normal distribution, which is most common choice. So when you have a good estimate of a parameter values, but so the first step you can take is to assume that its variance is proportional to its mean value. So for example, in HydroUQ, some of the default random distributions are provided by assuming that its variance is like 0.1 times its mean. So that's one thing you can do. And otherwise, if you have a good estimation on the upper and lower bound of parameters and have no other information, then choice will be uniform distribution. And for the log normal, it has like great property that the parameter value realizations will be always positive. So if you want to strictly limit your parameter to be positive, then this will be one of the choices. And then there's beta distribution, which is both lower and upper bounded, but it is non-uniform distribution. And then there is variable distribution that is also strictly positive, but it has like slightly different form from previous log normal. It might not be slight, so it has different functional form from log normal distribution. So this also can be choice when parameters are always positive. One widely used application can be when you have a random variable that represents a lifetime of a system, then this variable distribution is a common choice. And then there's converged distribution, which is also known as extreme value distribution. So this does not have any bound, but as you can see in this plot, it is quite asymmetric. So this distribution is widely used when your random variable is extreme value. That means, for example, when your random variables is defined and defined as maximum of multiple random variables or like peak response or something, then Campbell distribution can be a good choice. So, so now if you have you have all this information, including UQ and random variable in your user interface. So I will show you how Dakota runs its how HydroUQ use this information to run Dakota analysis and retrieve data. So this figure can be useful, especially if you want to, if your program gave you some error and you want to identify in which step it failed. So this is what happens when you click the Run at Design Save button. So once you click that, HydroUQ finds this text file called workflow applications.json. So this is basically the map that shows us where our backend applications are located. Dakota preprocessor is one of them. And then HydroUQ creates a folder to, before sending all these files to design safe high performance computer, it has to collect all the required files. So it makes a local directory for this purpose. So this is under remote jobs directory, which you define in HydroUQ preference tab. So here you first write dakota.json. HydroUQ writes this dakota.json, and then it launches Dakota preprocessor backend application. And then this preprocessor translates dakota.json into the actual Dakota input file, and also collects all the files that are required to run our workflow, and also the driver, like the scripts that actually runs this analysis. So, and then the processor notifies Hydro that all the files are ready. So Hydro zips all the file into a single file and then send it to design safe. So there is a copy of our input files. And then once everything is ready, it launches a job. So in current stage of HydroUQ, we first run CFD events separately. And then only after all these results are ready, we run Dakota analysis to quantify uncertainty inside structural like properties. And then once analysis is done, it will write the output file generated by Dakota. And it waits until user requests the file. And once get from design save button is pressed, now HydroUQ prepares another folder to get all these results, receive this result out file. And it actually copies all the file inside this file, this folder. And then HydroUQ reads all these files to display the results. So that's what you see in the result tab. So this is the slide prepared in my side. So I will hand over to Aakash to explain about like what UQ options we have in our app.
Thank you very much, Sangri. So we will continue the session with an overview of the different UQ options available in our HydroUQ tool. We'll essentially cover forward propagation, sensitivity analysis, and reliability analysis options. In forward propagation, let me just shift my zoom controls. Yeah. In forward propagation, the question that we are trying to answer is, given the distribution of the inputs, the random variables, which are inputs to our model, what is the corresponding distribution of the output quantities? So the input values are sampled from the probability distributions defined for them. And the computational model is evaluated at these input values to obtain the corresponding values of the outputs. So thus we get a sample from the distribution of the output quantities at the end of the forward propagation exercise. So in HydroUQ, we report some statistics of the output quantities to describe the distribution of the outputs. And we can also visualize the entire set of samples, not just the statistics from the output quantities. Now, so all the options that I'm going to discuss are available, are accessed through the UQ panel in HydroUQ. And currently, we only support the Dakota UQ engine. And as Sangri mentioned, we have plans of including more of the UQ algorithms that we are developing at the SimCenter. And so if the forward propagation options can be then selected by choosing the forward propagation option in the Dakota method category. So there is a typo in the word category, and I have a lot of screenshots showing the same word, so please excuse the typo. So under the forward propagation, there are currently 5 methods which are available, which are supported now. We'll go over all of these options except important sampling, which we'll discuss during the reliability when we are discussing the reliability methods. So all of these forward propagation methods, they generate sets of sample values of the input random variables according to their probability distributions, which are defined in the RV panel, as Sangri showed. And once we obtain sets of the sample values of these input RVs, we then get the corresponding sets of the output quantities of interest as a result of the forward propagation exercise. So if we can, to start off, we can select, I'll begin the discussion by the simplest methods, which is Monte Carlo or the Latin hypercube LHS method, which can be accessed here in the methods section. If these methods are selected, we just need to define how many samples we want to be drawn from the distribution of the inputs. And we can also specify a seed for the random number generator here. So keeping the same seed will help reproduce the same analysis. So the same the same samples of the inputs will be generated. And yeah, varying the seed will produce different sample values, and the results will be slightly different. Yeah, the same options are also there if you select Monte Carlo instead of LHS. This slide is just showing a comparison of LHS and Monte Carlo or the random sampling. So consider 2 random variables, and the domain of both is from 0 to 1. And let's assume they have a uniform distribution. Both of them have a uniform distribution. Latin hypercube sampling is a type of stratified sampling method where the domain of each of the random variables is divided into equal probability bins. And the number of bins is equal to the number of samples requested. So in this case, we want to draw 4 samples using Latin hypercube sampling. So the domain is divided into 4 bins. And the bins, or all of these segments, they depend on the type of the distribution. For uniform distributions, all the segments are of equal width, which is what we have in this case. Other distributions will have different segment widths. Latin hypercube sampling ensures that all the bins are selected once in each row and column. So if you see so the 4 bins along the domain of the random variable 1. So each have 1 sample each from the bin. And it's the same is true also for if we consider the RV2 axis. But the other option, which is Monte Carlo or random sampling, in this method, the samples are selected randomly according to the user-specified probability distribution. So you just see these 4 samples are just scattered at random in the domain. So Latin hypercube sampling spreads the samples around and ensures like full coverage of the range of the input variables, which frequently cannot happen when we are using Monte Carlo sampling, especially when the number of samples asked is very small. Now moving on to the other methods here. So this slide now shows what happens if we choose the Gaussian process regression method in HydroUQ. So this is a type of a surrogate model, and the other two sampling methods might actually need a lot of samples for the output statistics to converge to their true values. So in order to overcome this hurdle, especially for real world problems where the simulations are computationally expensive, Dakota has support for doing forward propagation using surrogate models. And some of those surrogate models can be accessed by selecting the Gaussian process regression here. And in these methods, fewer simulations of the expensive model is run. So for example, only 20 samples are requested from the expensive model, and the results of these simulations are used to train a surrogate model. Then we can draw a very large number of samples from these cheap surrogate models very quickly. So that way we can get more samples of the output quantities. But however, there is a caveat here. While the other sampling methods are robust and provide unbiased estimates, the error caused by using surrogate models is often very hard to evaluate. While we call this method as Gaussian process regression, it's not just Gaussian process. Several surrogate models can be accessed here, which are shown in the slide. So this is just a subset of all the options which are supported by Dakota. And if you want anything else which we are not supporting in the current version of HydroUQ, please make a feature request in the SimCenter forum. So here the surrogate training data for all of these surrogate models listed here is generated using either the LHS method or the Monte Carlo method. The other option under the method section was polynomial chaos expansion. This is actually just another kind of surrogate model. And the reason this is just in a separate category is we are not using LHS or Monte Carlo sampling in order to generate the training data, but instead we are using quadrature methods to generate training data. So that was just a very brief tour of all the options for forward propagation. Now we'll actually see an example where forward propagation of the uncertainties in the input random variables is done in a model where the water wave loading on the structure is obtained by conducting CFD analysis. So we'll quickly go through the options in the different panels for setting up HydroUQ. I will mostly touch upon the UQ options and only the, because other panels will be covered by the other presenters. So here we are choosing forward propagation, and for this example problem, I've selected LHS as the sampling method, and I've requested 1,000 samples. And this just shows the building information for the actual example that we're using. And in this example, we have two random variables which are defined, which is the floor weights and the story stiffnesses of the structure. And so these are two snapshots from the event panel. Excuse me. So this shows the setup for the CFD analysis. Here we are choosing a general flume to simulate the water wave loading on the building. And the other options are shown in this slide from the FEM, EDP, and the RV panels. So I'll not even go over anything in the FEM panel. It will be covered tomorrow in detail. And for this example, we're requesting standard EDPs. And in the RV panel, we are now defining the probability distributions for the two random variables which I have considered in the problem. And then once the problem is now completely set up, we log into design phase using the button in the top ribbon in the application. And then we click run a design phase button to perform the analysis. So Sangri has explained what happens when this button is clicked earlier in the session. And then once the analysis is finished, so if it takes a long time, so you can even like close the application once you submit the analysis. So now if you now again reopen the application, so you might need to log in again to retrieve the results, and you can get the results by clicking on the get from design phase button here. And then so that will open up the list of jobs. So you can then right click on the job that you want to retrieve the data for, and then you will be able to retrieve the data from your analysis. That will now populate your results panel. So the results panel until now was empty. Now it is populated with the results. There are two tabs in the results panel. The first tab is the summary tab. And this displays the statistics of the quantities of interest obtained after the forward propagation analysis. So for all of the quantities of interest, we see the mean, standard deviation, skewness, and kurtosis reported in the summary tab. And in the other tab, which is the data values tab of the results panel, so there is a chart area for visualizing the results, and also there is a spreadsheet area at the bottom, which shows all the quantities of interest, as well as the input quantities in the table here. Now we can plot each column in the spreadsheet versus the first column. So the first column is always the run number to inspect each of the sample values individually. And this can help to summarize the results quickly. And it might even help in debugging if you see that something is going wrong at a particular sample. So you can find out what sample run the things went wrong, and you can inspect what are the parameter values, and you can log into the work directory and check if something is going wrong. And so when you select a column of data in the spreadsheet area, the corresponding visualization gets updated in the chart area. And so it's also possible to save the data to a CSV file for further post-processing outside Coffin if that is desired.
Aakash, if I could just ask a question.
Yeah.
So what are these columns representing? This just quantity of interest you said. What do they mean, right? Because they say like some PID one, something like that, right? Like there are some short forms given there. So just curious what these are, maybe, if you might be able to elaborate on them.
Yeah. So it's actually not possible to see all of these because we have so many quantities of interest here. So, but there are 4 kinds of quantities of interest. So PFA stands for the peak floor acceleration. And each of these also has the corresponding node number as well as the degree of freedom from your model where the quantity of interest is extracted from. So PFA stands for peak floor acceleration. I think RMFA stands for root mean squared acceleration. PFD is peak floor displacement, and PID is peak interstory drift. So these will be explained in more detail tomorrow by Quanshi. But yeah, so these are all the standard EDPs which are defined in the EDP panel. So the other option is to actually extract quantities of interest where you can pass in another post-processing script as well as a script to record the corresponding quantities to a text-based file. But yeah, that is also a possible option. Otherwise, the standard EDPs are always extracted for each node in the structure, and they're always these 4 quantities. Okay. So here, by right-clicking on any column in the spreadsheet area, that will make that the x-axis in the chart area above, and by left-clicking on another column, that will be plotted along the y-axis. And so in this plot, we're actually just inspecting the RVs, the random variables. So here we are plotting we're just getting the scatter plot of the samples of the inputs, K versus W, the 2 random variables in this problem. Now from this scatter plot, we can make out that there are actually samples coming from a bivariate normal distribution, which is what we had defined in our RV panel. There is no correlation between the RVs because we haven't defined any correlation. And so there are 1,000 samples, and all of these are obtained by Latin hypercube sampling. Now by clicking on a single column, so if you first left click and right click on the same column, then you can display either the histogram or the CDF of that quantity in the chart area above. So here we see that we've clicked on W and it has a normal distribution, a bell-shaped curve as it should have. And you can also inspect the CDF for that same quantity. So in this plot, I'm just inspecting what is the histogram of the peak floor acceleration. So this is one of the quantities of interest in the problem. So this is the peak floor acceleration at node 1 in degree of freedom 1. And so here we can notice that there is a long tail of this distribution. This is not a normal distribution. And so you can also plot the inputs versus the outputs and get scatter plots. So here we are showing two quantities of interest plotted against the two random variables. So each row is that quantity of interest, and this is each column is corresponding to the random variable. We can observe that the peak floor acceleration depends on the value of the floor weight, but it does not show either an increasing or a decreasing trend as the value of the story stiffness is changed. And for the other quantity of interest, the opposite is true. We see that the story stiffness influences the peak floor displacement much more than the floor weight. So these pictures sort of qualitatively show that the output QIs are sensitive to one or the other random variable of the input random variable. And so this actually leads us to the next topic in today's presentation, which is global sensitivity analysis. Now, in this method, we are trying to answer this question. So given the distribution of the inputs, how influential are each of the input variables on the outputs? And this influence is quantified in terms of Sobol indices, which are returned by Dakota and which are reported in the results panel of HydroUQ. So this figure is a very similar, it's very similar to the scatter plot that I had shown earlier. So here we see that if the influence of the random variable is not too high on the quantity of interest, the expected value of the quantity of interest conditioned on any value of the random variable on the input. Actually, in this case, it is constant. So this is represented by the black line. And correspondingly, so the variance of this expected value of the QI conditioned on RV is very small. Whereas in the other case, we can see that the conditional mean is varying, and the variance of the conditional mean is much larger. So that brings us to this index known as the Sobol index, which is a variance-based sensitivity index, where this quantity is in the numerator. So we see that if this is high, the Sobol index will be high proportionately. So that shows a way of quantifying how sensitive to each of the input quantities is that corresponding output quantity. Now, in HydroUQ, there are two methods supported to compute the sensitivity indices. We can draw samples either using LHS or Monte Carlo. And the number of model evaluations is actually not equal to only the number of samples. It is equal to P plus 2 times the number of samples, where P is the number of input random variables. So this, I will now show an example of global sensitivity analysis, which is the exact same problem, but instead of doing forward propagation, we are now doing sensitivity analysis using LHS and requesting 1,000 samples. And now these are the results of the sensitivity analysis. So there are actually two Sobol indices which are reported in HydroUQ. So there is a Sobol index for the main effect and Sobol index for the total effect. The main effect index quantifies how much influence the random variable has on the quantity of interest by itself. The total effect index quantifies how much influence the input has when considering all the interactions with all the other input random variables. So we can observe that for the peak floor acceleration, the sensitivity index corresponding to the floor weight is much larger than that for the story stiffness, which is again what we had also seen pictorially in the scatter plot. So here we are showing that the peak floor acceleration is much more sensitive to the floor weight than the story stiffness. And in the bottom here, it's again the peak floor displacement for that node. And we see that the Sobol index corresponding to this input variable, the story stiffness is much higher than the value corresponding to the floor weight. So this agrees with what we visually saw, and this puts some numbers. It quantifies how sensitive each of those QoIs are to the input variables. And I mentioned that in this case, there are only 2 random variables. So the total number of samples, even though we had only requested 1,000, is 2 plus 2 times 1,000, which is 4,000 in this case. And so the data value panel is just, it's identical to what was previously discussed in the forward propagation case. And now, so for the peak floor acceleration, if we now plot the CDF, we observe the same thing. There is a long tail on the right-hand side. And so it is of interest to evaluate what is the probability that a certain value of the peak floor acceleration is exceeded. And this brings us to the next and the last topic of this talk, which is reliability analysis. So here we are trying to answer this question given the distribution of the inputs and some response or output level of interest. What is the probability of exceeding these response levels? And that can be computed by making use of the CDF. So it's a mapping through the CDF. And while this quantity can actually be computed using sampling methods, it's very expensive to do so, especially if the threshold values of interest are correspond to very small probabilities. So instead of using sampling methods, other specialized techniques are used, and those are the reliability analysis methods, which are implemented in HydroUQ in Dakota and available through HydroUQ. So these methods are all very efficient at estimating the statistics details of the response quantities. Now, we can again ask the inverse question. So given the distribution of the inputs and some probability levels of interest, what is the corresponding response or the output value? So that is an inverse sort of mapping, again, using the CDF or the complementary CDF, which is 1 minus the CDF. So if we select the reliability analysis method, there are 2 methods available, local reliability and the global reliability methods. And all the reliability methods work after making a transformation to standard normal space. And so this shows we can ask for either the probability corresponding to threshold response levels or the response corresponding to threshold probability levels. And so among the local reliability methods, we can choose an option known as the most probable point or MPP. And each of these MPP search techniques, they solve local optimization problems in order to locate the most probable point of failure, and which is then used as the point about which these probabilities are integrated to obtain the reliability, the probabilities. And here these are the different approximation. These are the different options available when you click MPP local search method. I'll not go over all of them. So if you select the no approximation method, and there are 2 integration methods. So these correspond to form and sum. So these are the most frequently used reliability methods, and that's how you can access them in HydroUQ. the last thing was global reliability methods, and global reliability methods are designed to handle multi-modal failure surfaces. And these work by developing a Gaussian process approximation, a global approximation of the response surface using Gaussian process models. And these Gaussian process surrogate models will accurately resolve a particular contour of the response function. So that corresponds to the threshold response values which we would have entered here. And then once they do that, they try to estimate the probabilities using adaptive importance sampling. And also, if the response surface, if the failure surface is multimodal, we can also use, it will use multimodal adaptive importance sampling. And yeah, I think I'm coming close to the end of my time. So this is actually, this is an end of the overview of the different UQ options currently available in HydroUQ. We are actively working to incorporate more UQ features in the application, and you can make feature requests in the SimCenter user forum. And if you want more details and also some guidelines for usage of all of these methods, please refer to the Dakota user manual. So it also it provides all the details for all of these methods, as well as some guidelines for usage of the several methods that we discussed today. Yeah, that brings me to the end of my talk. Thank you all for your attention.